Welcome students. In the last lecture we have seen unit 1 amplitude modulation. In today's lecture we are going to see unit 2 angle modulation. First we will see what is the comparison between angle modulation and amplitude modulation. Then we will dwell into what are all the types of modulation available. Then we will see what are the basic parameters we have to discuss and derive in the angle modulation. Unit 2 is angle modulation. It is coming under the classification of, in the previous lecture we have seen analog modulation. Whenever we have a carrier of analog modulation, whenever we have a signal, information signal in analog form, we will go for analog modulation. Whenever we have a signal in our information in terms of digital, we will go for digital modulation. In analog modulation we have, depending upon the types of carrier, if we have a continuous carrier, we will go for continuous modulation. If we have a discrete or pulse carrier wave, we will go for pulse modulation. This classification is depending upon the information. This classification is depending upon the type of carrier signal. So, in this continuous modulation, we have seen amplitude modulation in unit 1. In amplitude modulation, we have studied DSP FC and DSP SC, SSB SC and VSP. 4 classifications in amplitude modulation. In today's lecture, we are going to see the second classification coming under continuous modulation, angle modulation. So, this is our unit 1, this is our unit 2. Before moving into what is angle modulation, we will just compare what is amplitude modulation with our new topic, angle modulation. Our first topic is angle modulation versus amplitude modulation. Amplitude modulation. We have already discussed what is amplitude modulation. Amplitude of phase, frequency or amplitude of carrier is varied in accordance with amplitude of message signal. In angle modulation, in amplitude modulation only this amplitude is varied in accordance with amplitude of message signal. Here in angle modulation, phase and frequency is varied in accordance with the AM of message signal. Second, our modulated signal S of F is always an translated version of M of F. Translated version of our message signal or spectrum. We have seen if this is our message spectrum minus FM to FM in terms of single tone modulation, this is our M of F, our minus FC carrier signal C of F, this is our FC. So, our translated signal S of F is, this signal is shifted to here, this shifted to here. So, this whole spectrum shifted to FC and this whole spectrum is shifted to minus FC. So, that our signal will be minus FC, minus FC and plus FC, FC plus FM. Here FC minus FM, this is our lower side band, this is our upper side band. Here minus FC plus FM, minus FC minus FM. Here again this is our lower side band, this is our upper side band. S of F is always a translated version of M of F. Here need not be. We are going to see how it is varying from the amplitude modulation. Need not be a translated version. Third point which we are going to discuss is bandwidth, in terms of bandwidth. Bandwidth is maximum for double sideband full carrier as well as for double sideband suppressed carrier, twice the modulating frequency. Here, since we are going for frequency and phase changes, bandwidth is always, BW stands for bandwidth, bandwidth is always greater than 2 FM. The fourth point we are going to see is in terms of signal to noise ratio. Here we are having low signal to noise ratio because noise usually accumulate in the amplitude of the information. Here, since we are changing only the phase and frequency, our amplitude remains constant, therefore we are having high signal to noise ratio. Here we are having a trade-off. By consuming more bandwidth, we are offering high signal to noise ratio. Bandwidth and signal to noise ratio are trade-off factors. And the fifth one is amplitude modulation is a linear process. Here, it's a non-linear process. So, this is the basic comparison between amplitude modulation. We have already studied amplitude modulation. This is the angle modulation which we are going to cover. Now, we will move on to what is the definition for angle modulation. Angle modulation is the process in which angle modulation is defined as the process in which angle of the carrier wave is varied in accordance with instantaneous amplitude of the modulating signal, message or modulating signal. Keeping our amplitude as constant. Keeping constant amplitude of the carrier signal. Therefore, only we are changing the angle. Angle is in terms of frequency and phase. Frequency, phase. Only we are changing either phase or frequency of the carrier wave with respect to amplitude of your message signal. That is phase, frequency or phase is varied in accordance with the amplitude of your message signal. This is the definition of angle modulation. Now we are going to see what are all the types coming under angle modulation. Types of modulation. The two classifications are frequency modulation and phase modulation. If we change frequency of the carrier in accordance with amplitude of the message signal, then it is referred as frequency modulation, in terms FM. In short terms, we refer it as FM. If a phase of the carrier signal is varied in accordance with the amplitude of the message signal, then it is referred as phase modulation. In short, it is referred as PM. Before we are going to see what is frequency modulation and what is phase modulation, we will see some basic concepts. First, we know the unmodulated carrier signal is given by C of t is equal to AC cos 2 pi Fc t. This is our unmodulated carrier signal. Our modulated signal S of t is given by AC cos theta I of t. So, this is our modulated waveform. S of t stands for modulated signal. where theta I of t is given by 2 pi instantaneous phase. Theta I of t is equal to 2 pi fct plus phi of t, where theta I of t is referred as instantaneous phase. Instantaneous phase. Instantaneous frequency is given by Fi of t, which is equal to 1 by 2 pi d by dt of theta I of t. Instantaneous phase deviation is given by instantaneous phase deviation is given by phi of t. Instantaneous frequency deviation is given by one by 2 pi d by dt of phi of t. So these are all the basic concepts. The carrier signal is a rotating phasor of length AC and angle theta I of t. Now we will see what is phase modulation, then we will move on to frequency modulation. Phase modulation. We have seen the definition. Phase modulation is changing the phase of the modulated signal, phase of the carrier signal, or we can refer it as carrier signal, keeping our AC as constant, that is amplitude as constant. Only we are going to change phase of the carrier signal with respect to amplitude of the message signal, that is phase. We have seen what is the phase deviation. So phi of t is changing accordance with the message signal. By replacing the proportionality constant Kp into m of t. This is our instantaneous phase. Instantaneous, here this is instantaneous phase deviation. Now we are going to see what is instantaneous phase. This is deviation. Now we are going to substitute this phase deviation in instantaneous phase. We know the formula theta I of, what is our instantaneous phase? Theta I of t. Therefore theta I of t is equal to 2 pi fct and phi of t. Just now we have seen our instantaneous phase deviation is Kp into m of t. Therefore plus Kp into m of t. We have not defined what is Kp. Kp is phase sensitivity factor. Similarly, as we have seen, amplitude sensitivity factor Ka in amplitude modulation unit. Phase sensitivity of the modulator. It is expressed in radians or volts. Radians per volts. This is the unit for this proportionality constant Kp. Therefore, the time domain expression is given by time domain expression of phase modulation is given by Pm. AC S of S Pm of t is given by AC cos theta. This is the modulated signal general expression. Therefore, S Pm of t is equal to AC cos theta I of t. We have to substitute our theta I of t in this equation. Therefore, if we keep this equation as equation number 1, if we keep this expression as equation number 2, when you substitute 2, 1 and 2, we'll get S Pm of t is equal to AC cos 2 pi fct plus Kp m of t. So this is our final expression for time domain of phase modulated signal. Now we will see what are all the instantaneous frequency. We have seen instantaneous phase deviation. We have to now see what is instantaneous frequency. instantaneous frequency. What is the formula for frequency, the instantaneous frequency? 1 by 2 pi d by dt of theta I of t. We have to substitute our equation number 1 in this. Therefore, d by dt of 2 pi fct plus kp m of t. When you differentiate with respect to t, 1 by 2 pi into 2 pi fc plus kp is a constant. Therefore, d by dt of m of t. This 2 pi and this 2 pi will get cancelled. Here you will get again a 2 pi, okay, here. Therefore, our fi of t instantaneous frequency is given by fc plus kp by 2 pi d by dt of m of t. This is our equation number 4. What are all the features of phase modulation? Features. 1. Zero crossing of PM wave is not regular. Irregularity will be there. Signal will be irregular. Because we are changing only the phase of the carrier signal in accordance with amplitude of the message signal. Therefore, in the zero crossing will not be regular. And another one feature is envelope of the pulse modulated signal is constant. Therefore, we don't have to worry about the noise accumulation over the envelope of the signal. Since in amplitude modulation, only the envelope portion having the information. Therefore, if any noise gets accumulated in the envelope of the signal, our total information will get lost. Here we don't have to worry about the envelope of the signal because only the phase of the signal is varied in accordance with amplitude of the message signal. These are all the two features of phase modulation. Now we will see frequency modulation. Frequency modulation, in short term we refer it as FM. It is the form of angle modulation in which the instantaneous frequency is varied in accordance with the amplitude of the message signal. Therefore, we know that modulated signal is S of t. Therefore, S Fm of t is equal to AC cos theta I of t. We know this is the general expression. Therefore, carrier signal frequency Fc is changing in accordance with the m of t. Fc, this is our carrier signal frequency, it is changing in accordance with the message signal. If m of t is constant, Fc is also constant because we don't have any variations. If m of t is discrete, then Fc is also discrete depending upon the discrete value. If m of t is continuously changing, then our Fc is also having continuous values. We have just now seen what is the definition for frequency modulation. Our instantaneous frequency Fi of t is varied in accordance with the amplitude of the message signal. Therefore, Fc plus Kf into m of t. This Kf stands for the frequency sensitivity factor of the modulator, where Kf is the similar to Kp, which is the phase sensitivity factor. Here we are referring it as the proportionality constant, we are referring it as Kf. Since our carrier frequency will be same, only it is having either increasing or decreasing depending upon the message signal. Therefore, we will have a deviation over here. Kf is referred as frequency sensitivity factor. Frequency sensitivity factor. Therefore, we already know what is the formula for frequency deviation. This instantaneous frequency is given by Fi of t is equal to 1 by 2 pi d by dt of theta I of t. So when you substitute this, or by equating equation number 1 and 2, we will get 1 by 2 pi d by dt of theta I of t is equal to fc plus kf into m of t. We can bring this to 1 by 2 pi this side. Therefore, d by dt of theta I of t is equal to 2 pi fc plus 2 pi kf m of t. By integrating on both sides, we will get theta I of t is equal to integration of 2 pi fc plus integration of 2 pi kf m of t. Therefore, our final expression will be integral of 2 pi fc. Whenever we integrate in a constant term, we will get 2 pi fc t plus 2 pi kf integral over 0 to t m of t dt. This is our instantaneous phase. Now we have to substitute our instantaneous phase in modulated signal SFM of t. This is given by AC cos 2 pi fct plus 2 pi kf integral of 0 to t m of t dt. So this is our final expression for frequency modulation. Here again, in the future, we can write this envelope of the envelope of the modulated signal is constant. Envelope of the modulated signal Sm of t is constant. Therefore, noise accumulation will be reduced. Second, irregularity will be there in the zero crossing. Now we will see what is a graphical representation of FM and PM. This is our message signal. With respect to t, m of t, this is our carrier signal. This is a low frequency signal and this is a high frequency signal. So this is our C of t carrier signal. This is our frequency modulated signal SFM of t. Whenever we have a high frequency, we'll have a high frequency signal. Whenever we have this is our positive cycle and this is a negative cycle. So during the positive cycle, we have high frequency, and in the negative cycle, we have a low frequency. Therefore, the carrier signal will be the frequency will be changed according to this. Here we have high frequency, and after that so this period we have high frequency and this period we have low frequency. This is our modulated signal for frequency. This is for phase. Here, for a continuous signal, it is difficult to emphasize where we are getting the phase deviations. So, whenever we have a change in the phase of the message signal, here also we will get a phase change. So, the zero crossing across will be irregular. Here we have a phase change and here we have a phase change, but it is difficult to emphasize in which are all the places we are getting irregularity. But if we take a unit step signal for message information signal, now we have taken a unit step signal. So consider this as our m of t. So from this constant k value we are having 1. So here we are having 0 and here we are having 1. So this is our message signal. When we use a continuous carrier signal, here C of t. Now we can clearly visualize which are all the places we are getting the phase and frequency change. This is our SFM of t. So this is our no amplitude. Here we have an amplitude. So in this phase we are having high frequency. We have low frequency, and from this phase we are having high frequency. So this is low frequency part, this is high frequency part. In phase modulated wave, SPM of t. So this is our changeover period. So till this phase we are having the constant frequency will be maintained. So whenever we have a change in value in the message signal, the phase will be changed. In a continuous signal, it is difficult to emphasize the factor because for each and every particular point we are having a change in value. But here we are till this point k we have a 0, and then after this k we have 1 value. So therefore the phase variation is clearly visible in this type of unit step signal. This is a phase reversal period.